Screen share is paused. Okay, so welcome everybody. This is Chris Jones. I'm recording. Okay, good. I'd like to welcome everybody to the my Garden and Country Extension webinar series. Today we've got Dr. Janique Artiola to speak to us about biochar. He's going to be giving kind of a general introduction of what is biochar and uses for it here in Arizona and our desert and semi-desert soils. Okay, so a little bit about these webinars. They are a weekly Zoom webinar. They'll be 60 minutes or less. I'm holding them Thursdays at 11 a.m. They feature a variety of horticulture and natural resources topics relevant to the environmental conditions and environmental concerns of Gila County, Arizona, which may well be of interest to people living anywhere else. And a recording of this presentation will be posted at this website. Please go ahead and bookmark that website. I'm still learning it, but this is where the webinars will be announced and archived. And keep in mind that the University of Arizona is an equal opportunity, affirmative action institution. I thought I updated this. I did update it, but it's not the one I updated. So at this time, we're going to have Janique give a presentation about biochar. He's got about 30 minutes. And at the end of that, we will open it up for some discussion. This is the first time I've done this as a webinar as opposed to a meeting. So I'm going to ask you to go ahead and put your questions in the chat. I will try to, I can allow people to talk and unmute you as the moderator. So we're going to see how that works today. This is new. But definitely want to have that interaction with Janique and with your questions. It's always a great portion of this presentation. I've got a little poll we'll do to see how you heard about this. I've got an evaluation I'd like for you to share about, and we'll move on from there. So Janique is a professor at our University of Arizona. He is a water quality specialist and wrote a bulletin on biochar. And I saw that, I'm like, Janique, we need to be using more biochar. And so he said, I'm retiring, so grab me before the month is out. And so here he is. And I'm going to ask you go ahead, that's our introduction, to take over the screen, Janique, and put your slides up.
So I need to share the screen again. Hold
yeah,
on.
yeah.
Okay.
Start that all over. That's why I like to exercise it a couple of times.
Is it here?
Yeah, put it on full screen and you're set to go.
All right. Well, thank you, Chris. So we'll talk, it's only about 30 minutes and maybe less than that. We'll see how that goes. But I'll start with introducing a little bit what biochar is made out of. And since I'm a chemist, a couple of slides talking to you about chemistry. How it's produced, not that complicated. By the way, as we speak right now, there's a lot of biochar being produced up here in Pima Canyon. We have what, a 4,000 acre fire burning by Oro Valley. By the time it's finished, there'll be a lot of biochar produced, by the way. A little bit about characterization and then some greenhouse experiments that I conducted. I won't talk about lab experiments, but and then a little bit of summary and do's and don'ts based on my bulletin on your garden about biochar. Okay, so going back to what, 3, 4, 5, maybe pre-Columbian times, biochar has been, or facsimile of it has been incorporated in one way or another one into soils by native Central Americans and South Americans, and even and even the parallel evolution of, I guess, of societies. Go back to Australia, the Aborigines, there's also evidence that they used it. In my opinion, it comes from primarily burning, slash and burning and clearing areas for cultivation, and the realization that when you slash and burn and you release a lot of nutrients back into the soil, particularly if soils that are very sandy and light in texture. And I'll talk more about that. So basically, you've seen that before probably, but if you light up a match, you're actually producing biochar. There's a very nice profile in here that's worth remembering. You release a bunch of chemicals, hydrocarbons, volatiles, some particulates and gases that basically burn throughout the profile of a plume at various temperatures. And I'll show you a profile in a minute and why this occurs. And so at the end, you if you don't allow this match to continue to burn and you put it out, the black part of it is in essence charcoal. Is really nothing but charcoal or biochar. The area that hasn't completely been combusted, but there's been some chemical transformations that are worth mentioning that make biochar or char or charcoal quite stable. And in fact, if you go to the studies that have been done in wood forests throughout the ages, you can find traces of char buried multiple layers in forests, and that's how they can track the age of carbon and other things in places where there's been fires through char that lasts a long time. So here it is, your black areas. Again, don't let that turn into ash, otherwise you've lost your carbon. So a couple of slides on chemistry, which is very simple. Really, the chemistry of wood is basically sugars and a bunch of complex aromatic structures. So the sugars up here are what burns, what gives the flame, the colors, and the stuff that comes out in liquid droplets and in little particulates. It's mostly polymerized sugars. So as you well know, sugars burn and are used by our body quite quickly, metabolized. Of course, we cannot metabolize wood because the sugars are linked. But if there were monomers, we could actually metabolize sugars. As it is right now, only things like what do you call that? Termites can metabolize wood and turn it into sugars. They have the right enzymes. And so these little links can be broken, and then you've got your basic sugar. So that's what burns primarily. What's left, what doesn't burn very easily, is the lignin, the bottom here, which is basically a bunch of cross-linked but not fused yet benzene rings that are really, if you think about benzene being the stuff that's in your gas tank, and those benzene rings are connected through a bunch of oxygens and basic bridges, but eventually they'll fuse into something more stable, and that's really what makes the wood, okay? And so this is the final product. You do slow pyrolysis, and I'll explain that in a minute. You wind up with a bunch of cross-linked benzene rings that are quite stable. It's in essence graphite-like structure. So when you're burning wood, you really are producing natural graphite in a way. The more you slow burn, or the faster you burn it, or the more you can fuse those rings and make even more and more stable, longer fused benzene rings that are quite stable and very difficult to degrade, to break down, okay? So wood is primarily, I should say carbon, biochar is really primarily what's left, the benzene part of it, the lignin part that has been refused, restructured, and that's why it lasts hundreds and not thousands of years in our forests and in our soils. So how do you produce it? Quite simply, you can do open fires, but the open fires are quite inefficient because there's a lot of oxygen that comes in from below, and eventually begins to turn the ash, the wood into ash very quickly, and it's not very efficient. I don't recommend them. Another way is like my grandfather used to do, believe it or not, way back in Spain, trenches dug up in the size of, it could be any size of, any size, fill it up pack it with wood, light it on fire, and cover it with soil, and you come back a week later and you got your biochar. Kilns are very efficient. This is a standard Japanese kiln, which is very efficient. And the way it works is, again, you have to have an area where you don't have a lot of oxygen, because if I'm circling around here, because if you got a lot of oxygen, this stuff will continue to burn until it's ash. So as long as you allow the top part to burn, and there's flame, that's the sugars that are burning, then you're okay. But you have to allow the bottom part not to burn, so oxygen has to be limited. That's why those cones work very well. And then once the flame is put out, you can then quench fire with water, and then you've got your biochar. So it's a relatively easy process if you want to make it in large scale. Again, minimizing the production of of ash, because if you allow the ash to produce, then you basically have a pile of ash and not biochar. I produced it using a wood gas stove because I wanted a lot of control. Those wood gas stoves are great. They meter oxygen a little bit at the bottom and most of it at the top, so they are smokeless. If you want to really get BTUs out of your wood, this wood gas stoves are amazing. You can, they are amazing how efficient they are compared to an open fire. And this is a profile of the basically of the slow pyrolysis. That was about 15 minutes or something, or 20 minutes of burning. And you can see in here, if you stick the thermocouples down inside the biochar, is around 400, 500 degrees, which is called slow pyrolysis. And if you go up onto the top flame, it's quite hot and quite efficient at putting BTUs wherever you want them, boiling water, whatever you want to do. This is the result. So this, starting, for example, with forest waste that had been run through a wood chipper, and this is what you get, the various fractions that I got. So I had a lot of control because I wanted to make sure that I was characterizing each of those fractions and using them in separate experiments. But anyway, I'll show you here in a minute what happens with this material. But before we talk about that, there's a lot of talking about using this a lot and this and that. Yes, that we have a lot of woodland waste in Arizona. This is data that I collected a while back from a McDonald, and basically millions of tons of years of waste. Unfortunately, a lot of it is now being used and pelletized for wood stoves. There's this urban green waste that I was been very interested, because basically now a lot of it is turned into compost. Nothing wrong with that. In fact, I think it may be better. But there's tens of thousands of tons available, and that's your yard waste. And so I'll talk more about that. It's not as much as you think, though, compared to other climates. So this is a little bit about the properties. What is it made out of, and so on. So one of the problems with biochar, and one of the advantages, is that it's a very light particle. You can see in here that it weighs 10 times less than a soil particle. So a particle of char is good and bad in some ways. I'll talk to you about that in a minute. It's very light, okay, has a very high porosity, very high porosity, 80% or more porosity, so it can absorb a lot of water. But unfortunately, it has very high pH, and it has a fairly high salinity. Okay, that's the extract in here. Okay, and so it collects or stores a lot of salts, particularly calcium. You would think it would sodium. No, there's not a lot of sodium actually. It's mostly calcium and potassium that is stored by plants in our desert environment. There's a little bit of phosphate, phosphorus, and there's some micronutrients available. If you do a water analysis or an extract, which is what your plants would see if you were to put it in the soil, you'll see a little bit of calcium coming out, which we don't need. You'll see magnesium, which we don't need. You'll see sodium, which we need even less. You'll see a lot of potassium, which we have no deficiencies for at all here. And we have a little bit of phosphate, nothing to write home about, and not much. So it's not a very good source of elements that are of interest in our environment. Okay, those elements in here that I'm circling around are very good for wet, environments that have leached the soil a lot. But our soils are very rich in those elements. So biochar is not a good source, or is not an adequate source or needed source of those elements in our environment. I'll talk about nitrogen in a minute. Sorry about this thing. I don't know what happened to this. Must have gone out of whack. One slide that I wanted to show you here is it's actually what's called a moisture release curve. This shows you the experiment that I did with what's called Marana red rock soil, which is 95% sand. You can see in here that it doesn't hold a lot of water. But when you add biochar, when you add pine forest biochar, which is extremely water holding, you get this quite a bit more water holding capacity. I think that's one of the major advantages of biochar, that it holds a lot of water, or it can hold a lot of water. So those are experiments that we conducted very quickly, just a couple of slides on lettuce and on grass. And one of the things that we noticed on lettuce is the lettuce is very sensitive to salts. So the first experiment, fresh biochar with fertigation, we saw actually a decrease in yield when we applied 4% biochar to the soil. By the way, these applications are by mass, so kilograms per kilogram, okay, so 4%, whatever it is, in the topsoil, 6 inches. 2% gave a slightly higher yield, but not significant, and so on. But here we got an effect of salinity, too much salts. When we went to old biochar that had been leached and irrigated various times, we saw an increase in yield, but not that significant, okay, so suggesting that at least the salts were gone. And finally, at the end, we saw that if we fertilized and leached, but no fertigation following the first fertilization, the biochar actually held on to the fertilizer quite nicely. Even though there was a lot of variability, it held on to the fertilizer, it didn't lose it. That means that it not only stores water, but it also can store nutrients, particularly ammonia. Bermuda grass, that we did a little bit of experiment with that in terms of resilience. And what we found in here is that basically we stressed the Bermuda grass, and we saw that, yes, that higher applications of biochar would allow for the survivability of the grass, or the production of biomass for quite a while. So that's not significant. But what was important is that after 30 days, the soil that had no biochar, all the Bermuda grass was dead. And the 2% biochar had a 50% survivability, give or take, and 4% biochar actually allowed for most of the Bermuda grass to survive 30-day no water stress test. So that's the important thing. It did allow for the seeds to actually, for the roots to actually retain enough water to survive and not die after 30 days. The last experiment was here. Basically, we looked at a mix of desert soil, and we allowed those that mix of 11, 12, I forget how many desert plants to grow in the greenhouse, and we harvested them several times. And actually, we set for 6 months and 2 clippings. And we did see a significant increase in biomass production in the 2%, in the 4% biochar application in the clippings, suggesting again that biochar works quite well for your native landscape. If you have various native grasses, they will tend to survive a lot longer, just like Bermuda grass did, than without biochar. Oops, sorry. So that was pretty good data. The replications here are quite high, 8. One thing I want to mention is an important thing about biochar. That goes back to characterization, and so I'm going to spend a little bit of time on this because I should have put it before, but that's okay. Mass loss. So one of the advantages of burning wood is that you're losing about 80% of the mass. Now, let me show you here the sources. What I did in one of my last experiments, I wanted to characterize beyond pine forest waste. I also characterized mesquite, palo verde, juniper, Atriplex lentiformis, which is a saltbush, and tamarisk, which, as you know, is a salt-loving bush, and acacia, and pecan. And so you can see that when you burn that stuff after you wood chip it, you lose on average 80% of the mass. Okay, well, that's fantastic. That's why people go up in the mountains and in third world countries, and even in Spain back in after the Civil War, you would have people doing biochar production to sell it to the cities before we got the gas. I think it came from Northern Africa. We used wood chip stoves, or I should say biochar stoves. And so it's very light. The material is very light, and it retains about 50% of the energy. I didn't put it in there. So 50% of the energy is gone. You have 50% of the energy that you get. You lose up to 2/3 of the carbons. So people think that it's environmentally very, very, very good, but you are losing almost 2/3 of the carbons, depending on the material that you're burning. So that's a lot of carbon lost. Okay, not quite 2/3, a little bit less. But 62% is quite high on average. But the range, as you can see, is quite variable too, depending on the material. So a lot of mass loss. That's the water and the sugars that burn. A lot of carbon gone from the sugars primarily, and some from the lignin. The nitrogen is also lost. About whatever nitrogen is in the material. As you know, wood material is not very rich on nitrogen. It's about 1%, 1.5%, not much. But you lose about 60% of it. So whatever is left is probably not going to be plant available for years to come until some of that carbon mineralizes and the nitrogen is released. And so that's not very exactly, again, very environmental. If you're looking for a fertilizer for nitrogen, don't look for this. Now, as I said before, it will retain nitrogen fertilizer nicely, though. That's a good advantage, but it will not be a good source of nitrogen for you. One important thing in here, nutrient losses. That's something that hasn't been published, by the way, and needs more research. But I determined that, and 17 other elements, which I'm not going to mention, but the major nutrients, there is a 21 to 45% loss when you burn that stuff. 21 to 45%, excluding calcium. For some mysterious reason, calcium stayed there. But magnesium, potassium, phosphorus, zinc, iron, copper, zinc, molybdenum, a lot of losses. They were not there anymore. In other words, I measured the wood before, the composition of wood before, and the biochar before, compared the masses of absolute masses of the elements, and they were missing. They disappeared up into the air. It's known that some of those oxides are volatile. Iron oxides, zinc oxides, and other elements that are in oxide forms can volatilize during combustion. So they are, in essence, that's part of the pollution, by the way. Quite a bit of losses. Other elements that I'm not going to mention, actually, there were some of them environmentally relevant, like arsenic and mercury and things like that, maybe as much as 70% in some cases. So I'm not going to show you this data. This is still unpublished data. That's an average, again, composite of 8 different Southwest materials that people can use. So take home message, you are losing a lot of carbon, you're losing a lot of nitrogen, you're doing great on mass, and you're keeping 50% of the energy if you intend to use that again as a fuel later on. So summary, basically biochars can be produced from any sources of woody materials, you name it, anything that you can burn. Woody materials can produce biochar. I'll have a summary later on, a little bit later on the do's and don'ts of those materials, but the biochar production from green waste is obviously an exothermic reaction. That is, you can get a lot of energy out of it. That's a beautiful thing about it. But unfortunately, when we produce it, most of the time we just waste that energy. We release it into the environment. So it's a carbon negative source, meaning that you are storing long-term carbon, but it's only about 50% or so of the carbon that is stored, 40 to 50% of the carbon. The other 60% of the carbon is released immediately, which is not exactly what I wanted to know, or what I wanted to, I would like to keep it all if possible before releasing it, but it's not going to happen. Biochar application to light texture soils, sandy soils, will increase, no doubt about it, water holding capacity and increase your survivability of desert plants and some landscape plants like Bermuda grass, and it will reduce fertilizer losses. Whoops, sorry about that. What's going on here? It will reduce fertilizer losses. So those are good advantages if you plan to use that for landscaping or for areas where basically you're not going to disturb the soil. You're not going to be irrigating every time, maybe depending on seasonal irrigation or some, sporadic irrigation. So that I agree with. It does work for that. But do not look for biochar as being an important source of any other elements, because they are not needed, the salts. And secondly, nitrogen, for example, is lost and it's really not available from within. What I want to mention very briefly is the recommendations that I wrote down on the bulletin, and I think that's important. So one thing you should avoid if you decide to produce biochar is to avoid mixing yard waste. Keep them separate. They burn at different rates. They burn, some of them faster than others. Mesquite will burn a lot slower than, for example, pine or light grasses. So don't mix the waste. If you want to produce biochar, use single waste, and make sure that the sizes are even as possible to prevent excessive ashing. Use biochar when you use it at least a 1/4 inch or less small. Why? Why is that? Because biochar is vascular in nature. So if you take large chunks of biochar or charcoal, put it on the soil, it will not fill, the soil will not, the biochar will not fill up or saturate like a soil would. It will actually be empty inside. Why is that? Because water filters through from left and right, or from along the vascular length. And so there is a place where water doesn't go in anymore unless you soak it for months. I mean, not months, but days, and boil the water. It took me a long time to figure out how to actually get the porosity of biochar. I had to experiment a lot before I got the actual porosity, because water would not penetrate inside it. So biochar, for the most part, is actually an empty vessel. So you want to make particles as small as possible, but that creates another issue, which I'll mention in a minute. Soak the biochar overnight, if you can, several times before using it, and drain the salts. They'll prevent some shocks, some salt shocks that you might have on some vegetables if you decide to use it on your vegetable garden. Make sure you don't kill any of the seeds or germination or anything like that. So drain the salts is a good idea, because there is some ash on top of them when you produce it, and you need to wash that, and then you also extract some of the salts if possible. Make sure that they don't do any damage to any of your plants, seedlings. The ratio of biochar to soils can range from 1 to 100 to 1 to 10, but I would recommend that you mix it with compost. Compost has a lot of advantages, which I'm not going to talk about. I think somebody else did already. By the way, compost is not also environmentally friendly 100%. Compost also loses a lot of carbons during composting, maybe as much as 50% in some cases. So it's not also an environmentally friendly system of mixing things, but it's better, in my opinion. It could be better than biochar for our soils at this point. Biochar use biochar in soil backfills, in other words, in potting mixes, or better yet, with compost mixes. Keep biochar in the ground where it's not easily airborne. Again, go back to the fact that biochar is 10 times lighter than a particle, soil particle. What does that mean? It means that it will go airborne very quickly. So what you don't want to do is have biochar, small particles of biochar exposed on the surface of a soil while you're rototilling a dry soil. You're going to see a lot of stuff coming out into the air. So keep it in the ground. In other words, bury it, use it for landscaping, things like that. When you rototill your garden, make sure that you do it when it's wet. And never dry, and so on. So again, I'm concerned about people using this material in our dry environment because of the lightness of the particles. Biochar materials must be handled outdoors and stored and sealed in bags. Avoid dust exposure. Again, they are the material that's there. Remember what I said: benzene, and other aromatics. They're not exactly friendly to our body. So keep the dust exposure to a minimum. Wear masks if you have to produce a lot of it, and avoid disturbing the garden soils when dry limit to limit dust exposure. Do not add biochar to top mulches, again, for what I said before. And finally, a couple of publications in here. One that you're already familiar with, this bulletin that I recommend you take a look at. And then there is a more serious publication or summarizes some of the experiments that I showed you before. And with that, I'm going to open it up for questions. I think I kept it under 30 minutes. Chris?
Thank you very much. Okay, there I am. Okay, good. I'm going to open this up for questions in just a moment here. Got a couple of things going on. This is my first webinar as opposed to a meeting. So I'm going to ask people to respond to the chat. Go ahead and put the name that you have in your participant, where I can see your participant name. And that way I can unmute you and allow you to ask that question. So I've got a few names coming on here. Those will be the first I'll go to, and so I'll open that up to them in just a moment. I'm going to open up the one thing here. I just sent you an evaluation form. I might send that again because we're going to populate this, but if you can take a moment to open that, it should only take about 2 minutes to give me a little feedback on how Janique's presentation went and give me some advice on things we can also do. I also want to promote to panelists. Where'd you go, Darren? Darren McAvoy is next week's presenter who's going to talk some more about biochar and kilns and how to make biochar and how and some of its wildland-urban interface types of applications. So this was excellent, Janique. And I wish that I had a, I'm looking at what the participants can do. Usually there's a little response and they can applaud. So I'm sure there's wild applause going on that we just can't hear it. One of my interests and first things that I'm going to ask, because I get to ask first, is particularly those turf grass opportunities for using biochar. When I think about it, I think about some of those salt issues and nitrogen issues that come along with it, that when we're using turf, we control so many of those types of variables. And so would it be something that particularly in our arid climate that we can be using in the turf industry that's going to be able to lower the water bills enough to make it a worthwhile effort and venture?
I think so. I think it's a very good place to use it because it would be buried, for one thing. It could be layered. It could be mixed in, depending on your needs. It will leach out the salts quickly, but at the same time, it can also retain enough nitrogen, perhaps, to give plants, give them a boost. And of course, the water holding capacity. So I think it's a prime candidate to be studied. And also, more importantly, to actually play with the sizes of the biochar, which ones would be best under, as you know, turf grass is managed very carefully in terms of sand sizes and sand mixtures, right? And so for infiltration rates. So that would have to be studied. It would be really a nice project to play with, to adjust to replace, in other words, some of those sands that don't absorb anything, don't retain anything for biochar, which would give still the bulk that you need. It would also add some softness, by the way, to the turf, because this material is crunchy. That could be a negative thing. It could disturb. It could actually break up under pressure. Okay, it's not a grain of sand, so it will fall apart. So, but I think that's an area that should be explored more, and because I think it would be safe, very safe to apply, because it would be buried always under the turf. I think it's something that should be explored.
Thank you. And another thing I really appreciated was just kind of that airborne PM particular matter.
Worries me a little bit here in the Southwest.
Yeah.
It worries me a little bit, and that's why I'm encouraging people not to use it, you know, in areas where it will be exposed to airborne events, you know, wind.
So I've got Michael Chamberlin as a first question. He asked, please compare biochar utility with perlite, vermiculite, and pumice. Michael, I've unmuted you so you can speak.
Hello, Janique.
Yeah.
I was interested in if you might be able to compare the utility of biochar as a soil amendment with some of the mineral-based soil amendments that we may be more familiar with, such as perlite, vermiculite, and pumice, which are all a lightweight soil amendments that also are known to have water holding capacity.
Yeah, that's a good point. Well, remember, I skipped a few slides in here because I knew it was time, but one of the big advantages of people have been touted biochar to be above anything else is, first of all, because people thought initially, at least some of the people in the East Coast that are promoters of this, that we could use biochar as an additional source of carbon credits and to trap carbon permanently in the soil. So that obviously the other materials can't compete with. But is this significant enough? Probably not. Okay, but I'm just adding that. When it comes to structure, biochar is more brittle than those materials, particularly the pumices. The perlite is pretty flaky, but they are all good sources, as you know, of things like potassium and calcium. But who needs potassium and calcium in our desert environment? We don't. So that's one of the negative things of biochar, that you need to get rid of enough of those salts. And I think that's easy to do, by the way. It's not like it's complicated, okay? Just a few rinse cycles and you're done. But that's a negative thing, that you have all these salts in there you don't need. Beyond that, beyond the fact that the particle is more fragile, and again, I wouldn't recommend that you mix it or rototill or anything like that, as little as possible, and it can go airborne very quickly because it's a lot lighter, I think, than perlite. I don't remember what the density of a particle of perlite is. Pretty light though. But this material is quite light. I think as long as you keep it buried, you're okay. So, you know, they can compete with one another. If you could produce that stuff cheap enough locally from bio waste, then they could compete with one another, I think. Does that answer your question? I'm sorry, maybe you needed something else.
Yeah, that helps. Thank you.
Yeah.
Okay. Next question on the list is from Ariel Mark Ledger. It looks like they just dropped off, but it's a good question. First, they said, thanks for the talk. And the question is, when you tested the effects of biochar in addition on desert species, did you conduct a resilience test to assess the ability of biochar to increase plant survival?
On the desert species, I did not have the time. No, I only looked at biomass. No.
All right. The next question is from Richard Johnson, and I see he's ready to go. So Rich, you're up.
Okay. I was curious, you mentioned that the pH factor is pretty high with this stuff. I live up in Payson, and the soil in my yard is fairly high clay as opposed to the high sand contents of the deserts, the lower deserts. So if I'm going to use some of this stuff, how do I counteract that high pH factor? I'll still need to reduce pH here as well.
When you leach the biochar, and it's easy to do, just take a 5-gallon bucket or whatever, put some holes in the bottom and fill it up with water and let it drain slowly 3 or 4 times. That's how I did it. You will also lower the pH because the alkalinity and the pH are linked together. But when you wet the soil, what happens is that actually biochar reabsorbs a little bit of carbon dioxide from the atmosphere, believe it or not. It's a small amount, but it does absorb some carbon dioxide back, kind of like cement. Think of cement. And so, so that reabsorption lowers the alkalinity from about anywhere from 9 to 11 down to about 8, 8.5, which is okay with soils. But that takes a few days of wet, dry cycling and aeration. But as long as you do that, you, in other words, age the biochar. I call it aging. The word never caught on, but it's called aging it a little bit. Then you lose that high impact that the biochar has initially on the soil pH very quickly. So that shouldn't be a problem, okay?
Anything else, Rich?
Yeah, I did have one more question on, I see that you did some work with lettuces. How about some of the other vegetables? I'm a big vegetable gardener, and so I'm growing the tomatoes and the zucchinis and various other squashes and peppers, et cetera, et cetera.
I did not, but lettuce is one of the most sensitive plants we have. So basically, and we grew it from seedlings, from seeds. So if you do seedlings, it should be less of a problem. And if you basically have diluted that biochar as you should quite a bit, and even perhaps even mix it with compost, it shouldn't be a problem at all. Okay, with your tomatoes at all. Okay. I wouldn't say that. You could also test it initially on your greenhouse if you grow your seedlings, your tomato seedlings from seeds, unless you buy them. And then because that's at the stage where plants with vegetables are most sensitive to salts anyway. We did some experiments with monk seeds and lettuce seeds, and the monk seeds were a little bit more resilient than the lettuce seeds. Lettuce seeds are quite sensitive to salts, but that's only when you start from a seed. Okay, when you start from a seedling, a grown seedling, it's much less of an issue. Salts should be less of an issue. And again, they will be a temporary thing. It will not last very long.
Okay, thank you very much.
I'm going to do a little follow-up on that, Rich, in that you gave this wide range where it was as little as 1 to 100 for its application rate up to a tenth, 1 to 10% to 1 part to 10 parts mixed with compost.
Yeah.
So to me, that seems like a huge portion, but I mean, if it works, it works. So as long as it's been.
And thank you for the question. I think anybody who does obviously gardening and should never follow recipes of any kind. You should always do your own trial and error. Okay. And so you never start with, okay, well, he says 1 to 10, let's dump 1 to 10. That would be crazy. No, you always need to phase in this kinds of novelty things because your biochar will be different from my biochar. One of the things about biochars is they're all different. Okay, and you notice the range of variables that I saw on the last table of variability of carbon loss, of nitrogen loss, of elements loss. Same thing with salts, if I had put that data there. So there's a lot of variability. It depends on the size. The smaller the biochar particle, the faster you lose the salts. The bigger the chunks, the slower the salt will come out. A lot of different variables can impact your overall effect on the soil. That's why you need to start slow. Okay, you need to phase in that approach. If it works, then add a little bit more. If you like it, okay, go ahead and add more the following year, the following season. So, but yeah, there is no such thing as a hard and fast recipe to start from. There's way too many variables in this equation.
Good. Okay, so Chris Tetzloff asked the next question, just asking about getting a copy of Table 1 for future reference.
It'll be on your. By the way, this is unpublished data. Which table are you talking about? I'm sorry.
Well, she can clarify. I will.
One that has the basics of biochar.
Oh, that's in the publication. You can download the publication, or Chris can link to it, right?
Exactly. When I have an opportunity to archive this, I will include links to those two presentations he mentioned at the end, or the 2 papers.
Right.
Great.
Okay.
Okay, Kai, you are up next here, so you can unmute and yeah.
Sure, thank you. Janique, sorry I missed a lot of your beginning parts, but regarding the salts, we have a problem with the sodium salts for turf grasses. You mentioned turf grasses had a potential use.
Yeah.
And because the sodium is so high, we're using a lot of gypsum. And you mentioned that there was gypsum magnesium.
Yep.
What are the ratios? How high is the sodium content in the biochar relative to, say, calcium, magnesium, and the other salts?
Much lower, much lower, much lower. That's the good news. The ratios are maybe 1 to 10 at the most, or even higher than that in terms of sodium to calcium. Calcium and potassium are primarily absorbed by our plants. The data is quite clear on that, all the species that I tested, okay? So look at the table, the one of the tables that I showed at the beginning, and that was pine, okay? But other species, ponderosa pine, other species that follow the same trend, okay? Sodium is not absorbed very well, which is good. Those are not halophytic plants, the ones that I tested. So except for the, there was one actually there, actually none of them. Excuse me. So maybe the tamarisk, I'm sorry. But I noticed that even the tamarisk doesn't absorb nearly as much sodium or potassium than calcium. So yeah, it's interesting that the divalent ions are favored in terms of absorption by plants. So you shouldn't worry as much about the sodium, the residual sodium in there. And if it's there, it will be leached quite quickly.
And we can offset it with the gypsum applications as well later on then.
Right, you could potentially do that. And actually the calcium, you will have some calcium coming out of the biochar, which is a positive thing for you.
That's something that would be a benefit because it would help eliminate the or displace the sodium content.
Exactly,
exactly. And then the longevity of the product, if you apply it, say right now in the summer, how long does that last?
Well, the biochar itself is, as you know, is carbon that will last hundreds of years, okay? So that's as much as we know. It's pretty well documented. There is no evidence that it'll break down very quickly. It'll break down very slowly peripherally. In terms of the salt effect, it's going to be temporary. It's going to be, in other words, the amendment, the salts will eventually leach out, some of them faster than other ones, depending on your leaching regime. If you have a leaching regime where the waters are, where you're constantly leaching the profile to maintain the low levels of salts, then the salts will eventually disappear below the profile. And so you will not have any more in there. You'll have to add more, like you'll have to add more gypsum because you're losing it. So it's a temporary effect. But remember that originally biochar was designed, or people who began to use it in ancient times, they used it in light textured soils in hot climates, wet climates, and the slash and burn basically gave them, and the residual carbon in there, the biochar gave them those very, very wanted salts that they needed for their plants. We don't need those salts here. So the faster you get rid of them, the better off you are. So the benefit from biochar should not be from adding salts to your soil unless you have a very specific application, because even that will be very temporary. And there are much better sources of salts, particularly divalent ions such as gypsum, that you should be using instead.
The other part is you mentioned that it has the water holding capacities. So if it has the water holding capacities, we'd be applying less water, which would reduce the leaching.
Somewhat,
would
yeah.
That happen?
You would still see leaching through the macropores, okay? Through the macropores, because remember the porosity of biochar is quite small. I didn't tell you that, but the pores of the biochar, the vesicles are quite small. They're much smaller than many of the soil pores. So they fill out and then they release the water, and the salts get trapped on the edges, and then the salts get washed down in the first flush. So it's kind of a rinsing process. That's why I said you can rinse the salts out of biochar quite easily by doing the trick that I showed you before, which is actually explained on the bulletin too, of the biochar. Once they're gone, unless you put them back in there for some reason, okay? Or you go back into an arid regime of salt accumulation because you're not watering enough. Does that help you?
Yeah, I'm just trying to sort out in my mind how our turf guys would utilize it, because
I would think first, two things. First of all, I would try to replace some of the sand size materials that you're using now while keeping the same infiltration, but then realizing that those little cylinders will act as not only as moisture retention without really adding too much salt to it, but it will also retain some of the ammonia that you guys use, ammonium salts, particularly ammonia, not nitrates. Nitrates will not be absorbed by biochar, not at all. But ammonia will. And so you will have less losses of ammonia, less losses of nitrogen that will be released again. But it will not, in terms of the amount of biochar you'll be using, you won't be using a lot. You may be using 1, 2, 3, 4% initially and see how it goes, maybe increase it. That's not a lot with comparison to the amount of soil that you have, inert soil you have around it, okay? Think in terms of percentages, okay? So you're not adding that much salt into the system to begin with, okay?
Okay, that helps a lot because
Yeah.
I'm just trying to envision how these guys would apply it. So it would be like a dusting.
No dusting, no dusting, please. No, you would have to experiment
I
with.
mean, it's just a light application of the
Yeah,
product.
but below the surface, please.
So how do we get it under the surface then? I
You would
mean,
have to do it when you do your turfs. When you do your turf grasses, you would have to apply below the surface, maybe with some of your clawing system, or maybe some.
So if we aerify and punch holes,
Right.
that would be an ideal time to at
Exactly.
least get
Very
some of
good.
it introduced.
Very good. That would be an interesting experiment to try. Yes.
a lot
And
of
then what our guys do is they would top dress with sand. So we could incorporate that with sand.
You could apply it first and then top dress with sand. That would be my preference, because I don't want to see that stuff anywhere near the surface.
I noticed that turf is often sold, as kind of the carpeted turf. And that would be an opportunity to get it under the surface.
Exactly.
It's laid down. Would we
Good
be able
idea.
to apply that directly to those roots so that when we lay
Right.
it down, it's already there?
Yeah, you could do that.
Okay, so as a preparation operation prior to sodding a
Right.
site.
Right. That could work.
Interesting. That would be a real value-added type of opportunity, it seems.
So
you've got
to
'em
an existing turf site, it would be a lot difficult to do then.
Well, your idea of aerating seems like the way to
Yeah.
inject it. So Rebecca, you are up next.
Hi there. So
Hi.
is activated charcoal chemically the same as biochar?
Yeah, it's pretty much the same. Yes, it's just a big fancy word that people began to use. Okay.
Okay. So when we use activated charcoal for herbicide damage,
Wait. Activated. You said activated charcoal?
yes.
No. Activated charcoal is different. Activated charcoal has to undergo a series of steps that are quite expensive. So
Okay.
for example, you take coconut shells and you burn them, kind of sort of, you burn them under a much better controlled pyrolysis, probably in some closed ovens. Then you take that coconut, the coconut char that looks very much like charcoal, and you undergo treatments that include what's called high acidity treatments and high temperature treatments. We're using some chemicals which basically further expands the pore sizes of the materials. That means that now your coconut char that would cost maybe a cent a pound now will cost $1 a pound, because you've had to do all those treatments. So yeah, activated charcoal is basically the child of the biochar. That is that the biochar starts with basic charcoal, but then you need to go all those treatments that are quite expensive. That's why activated charcoal is so expensive, because it requires a series of physical and chemical treatments, including steam treatment, alkali treatment, I forget how many more, to expand the pores, the vesicle pores, to make the material even more porous.
So will biochar absorb herbicides in the soil in a similar?
It will. Yes, it will. We conducted the research on atrazine, and it will absorb atrazine quite nicely. Of course, not nearly as much as if it was activated charcoal, but then again, it doesn't cost nearly as much. It will also absorb TCE, will absorb benzene. It will absorb a series of organic contaminants. Yes, it will. That how much will depend on how much you apply and when you apply it and so on. Yes, but it is as one of the research areas that still goes on. I've done some of it. I haven't published the data. I may never publish it, but I do have some data on atrazine and a few other chemicals that are organic chemicals that we saw that TCE would absorb. I mean that, sorry, that biochar would absorb. Again, not as efficiently as activated charcoal.
Okay, that's really interesting. Thank you.
Yeah.
Thank you, Rebecca. And thank you, Janique.
Yes.
You can see that you've had an engaged audience. So
Yes, I have.
great questions, people very interested. This has been, we're up over 30. This is the best attended webinar I've held so far. So thank you so much. I've got a couple of things I want to finish up before we get off, and my goal is the next 4 minutes, 11:59. But if we go over, it gets fine. I entered the evaluation link one more time in the chat. That'll take 2-3 minutes max, so please get that information to me. I've got a quick poll I'm going to launch, which is just simply, how did you hear about this webinar? Did you get an email directly from me? Did you get one that was forwarded? Did you see it on Facebook? Newspaper, word of mouth, or other. So just going to help me to be able, how I'm getting the word out about this, and my efforts are valuable. Ooh, okay. Rich has one more question, and I wanted to give Darren McAvoy, who's next week's speaker, kind enough to be with us, just a minute to introduce himself and get us ready for next week. But Darren's going to follow it up for us. So, Rich, you asked, is there a benefit to soaking biochar in compost before adding it to the soil?
In compost itself, dry compost, no, but probably in some liquid compost that has a lot of nutrients, yes. Yes. Because it will absorb some of the ammonia that you might lose. Okay, if compost has a lot of ammonia, particularly if it's fresh compost and has some liquid in it, you will absorb and retain some of that ammonia, no doubt about it. Okay, so yes, that would be a good idea, and it's been tested before. I haven't tested it, myself, but mixing the two things initially and allowing them to age for a while. Again, I would recommend after you leach the salts, would be a great idea to absorb some of those, some of the ammonia that you could lose otherwise from the compost.
Great. Darren, you can go ahead and turn on your microphone. You got your mic on, so you can go ahead and you can turn on your camera too if you wish.
Okay. Let's see, where do I do that?
Your little icon on the bottom left.
Bottom left, start video. Okay. Tried. Can you see me? I don't see me.
That's okay. Go ahead.
Okay. My name is Darren McAvoy. I'm an extension forester from Utah State University. And Chris was kind to invite me to follow up Janique's excellent presentation next week on biochar production. I work with a bunch of simple kilns that I've been promoting and using here in Utah and around the West for the last 5 or 6 years. And so we'll talk mostly about making biochar next week.
Great.
Okay, there it is. So thank you very much, Darren. Please join us again. And gosh, everybody, we're right on time here. So thank you for all your time today, for joining us. And please help me to keep promoting this webinar series. And we look forward to seeing you again next week.
Thank you, Chris.
All right.
Good job, Janique. Good job, Chris. Thank you.
Thank you all.
Bye.
All right. Bye-bye, everybody. Whoops. I'll turn off the recording.